Today's goals are to learn how to construct test statistics, identify rejection regions, appropriately write and evaluate hypothesis tests. To do this, we're going to have some vocab: hypothesis test, a test statistic, rejection region, critical value, mutually exclusive, and exhaustive. We'll go over a brief primer on hypothesis testing using a non-numerical example. Then we'll discuss some two-tailed hypothesis tests. We'll end on some one-tailed hypothesis tests, and then go over homework. So in order to think about how we're actually going to conduct a hypothesis test here, it's going to be useful to think about how it is we go about getting new information about what happens in the world anyway. So generally speaking, people kind of go through life with a model of what the world looks like in their heads. And by a model, I just mean this is a way of sort of interpreting data that comes to them all the time. It tells them how they're going to process new information. And so anytime I go out in the world and I see something new, I plug that information into this model or the way I sort of view the world and see if it matches sort of what I expect. And if it doesn't, we've either got to conclude one of two things. Either I just happen to see some fluke thing that really doesn't change the way I view the world. I just saw some sort of idiosyncratic difference in the way I view the world. Or the data itself is so undeniably correct, this new thing I've just observed, that it makes me reconsider how I have been viewing the world to begin with. That is, that my model needs to be updated. The things that I am perceiving or how I've been interpreting information has been incorrect. And so the further is the piece of data from what I would have expected, the more unlikely, the more extenuating the circumstances must be in order for me to rationalize how my model could still be correct, and I happen to observe some really weird piece of data. So in that sort of a situation, the farther the data is from what we would have expected to see, the more likely it is the model was wrong to begin with. So to get this point across, we're going to start with an example of an experience I'm sure you guys have all had at some point. We're going to talk about me and my coworker, Dave. We're really, really close. And when I first took this job, he was really good at making sure I had a good sense of what was happening in my new workplace. We hit it off really well, so we've been hanging out a bunch. And we ended up having this big project we both needed to take care of with a pretty strict deadline. So he and I talked at a ball game one night and then had a discussion about how we were going to get this project done. So Dave texts me and says, "Hey, I had a great time at the ball game today, but I feel a little bit sick." Well, that's because he ended up eating 9 hot dogs on a bet with a stranger at the ballpark. And he tells me, "Well, I don't think I can really, I can't tell you how bad I feel. I can't even get out of bed. I think one of the hot dogs was bad. Can you handle the project without me today?" Now, I've got no problem with Dave. He's been helping me out from the beginning. So of course I have no problem, covering for him and making sure we can get some headway done on our plan for the project. This is a really simple way of thinking about how we've just tested a model. My model tells me that the piece of information I got about Dave, that he wouldn't be there for this project, isn't some big piece of information that's going to cause me to reevaluate my relationship with Dave. It's just simply, he's sick. This kind of thing could happen to anyone. I mean, who hasn't gone to a ball game and accidentally eaten 9 hot dogs? In short, the piece of information we saw about Dave's reliability was subject to sampling error. Okay, if I had more information about Dave, I would be able to wash out this one little piece of information that seems to suggest Dave isn't reliable. So after work, I follow up with him and ask how he's doing. Offer to swing by with a beer so I can catch him up on what happened. And it looks like Dave is still feeling sick, so he has really no interest in catching up and says, "Let's just try this again tomorrow." So the next morning he texts me and tells me, "Hey, unfortunately last night I got mugged when I was going out to get some medicine for my nausea. I got beat up pretty bad, so I won't be in the office today." Of course, I'm worried about him, and so I ask if I need to bring anything by, or which hospital he's at, and he says, "No, he's not really at a hospital. He's just going to sleep off his beating." So I tell him, all right, I'll go back into work today. I'll work on the project and I'll update you at the end of the day. Poor Dave. First, he got sick. Then he was too ill by the end of the day to go have anybody drop off and make sure he's okay. Then he got mugged. Poor Dave. All right, it's after work the next day. I've got a good feeling we're going to be able to crush our presentation. So I text Dave and make sure he's feeling a little bit better, try and give him an idea of what the plan is going to be. And he follows up by telling me he forgot to tell me that his mom had called and his favorite pet goldfish had died from when he was a little kid. It just finally died. And so he can't come into the office tomorrow and help with the project because he's got to go home and show his respects. And this is the moment when good old Dave, my buddy, turns into Dave the unreliable liar from work. This is just a very simple example of how once we get enough pieces of information, the likelihood that we are observing sampling error becomes less and less and less probable. So our first instance when he bailed on work the first time, that could have been sampling error. But the next 4 times in a row with less and less likely outcomes makes it really unlikely that Dave was reliable to begin with. Is it possible that he had a really bad string of luck exactly when I needed his help the most? Is it possible his goldfish is actually a 100-year-old koi that had been passed down through 3 generations of family and it was his last link to his extended family? Of course, it's possible, but it's not very likely. And this is the basis for a hypothesis test. With a hypothesis test, we will never be able to say anything with data with 100% certainty. We will never know for a fact whether Dave is a liar or just really unlucky. But at some point, the odds that he is just that unlucky become so implausible that I'm willing to settle on the fact that he's probably just a liar and move on with my life. In general, hypothesis testing is always going to be the same 4-step process. We're going to clearly articulate our beliefs about the world and collect some data. We'll compare that data to what we should have observed if our beliefs were correct, and then determine if there's some sort of discrepancy between our beliefs and the data that would cause us to change our mind about some population characteristic. So let's just do this in the context of our last example. Our baseline belief here, our null hypothesis, is that Dave is a really good guy. We have a lot of interactions with Dave related to work, and we compare the data. That is, we calculate some measure of our interactions with Dave, where we find out Dave happens to be absent a lot. But given that given our beliefs that Dave was a good guy, we would not expect to see this outcome. He should be around and be reliable. And now we're just left to determining whether these 2 things are so incompatible that we have to change our idea about Dave. And after our 4th example there in the goldfish incident, we determined that Dave is implausibly absent, that data is too inconsistent with my idea that Dave is a good guy. And as a consequence, I reject the null hypothesis and instead take on the new view that Dave just sucks. So what we're going to do now is transition this intuition on how this hypothesis test works to an example of what we're going to call a 2-tailed hypothesis test involving data. So it's going to be the same set of steps here. We're going to clearly articulate our beliefs about a population with 2 statements. One is called the null hypothesis and the other is the alternate hypothesis. And we'll write this as H sub 0 and H sub A. You may also see this as H sub 0 and H sub 1 in other textbooks. We're going to go out and collect some data and calculate a statistic from that sample of data. We're going to compare the sample of data to what we should have observed in the population to see how likely the 2 are to relate. And we're going to determine what's called a rejection region, which are the set of values for our sample that are so implausible to have come from the particular population that we have to reject our beliefs about this population. And this is going to be determined for us by the central limit theorem. Then what we're going to do is basically just determine whether that sample falls in what we're going to call the rejection region. And if it does, we're going to reject the null hypothesis. If not, we're going to say we fail to reject the null hypothesis. So let's give an example of how this would work. We've got a restaurant that I've been ordering a lot of takeout lately, as I'm sure many of you have. And so one of the things we run into is how long it's going to take them to get food prepped or get it delivered. And so one of the restaurants nearby says it would take them 30 minutes on average. And we figured out the standard deviation is about 10 minutes on every one of those orders. And so, it's good food. So I ordered it 25 times probably in the last 5 months here. And on average, across all those 25 times, it's taken them about 35 minutes. And so I'm willing to give them the benefit of the doubt, but the more pieces of information I have, 25, 30, 40, 50 times that I order, the more the discrepancy between the 30 minutes they promise and the 35 minutes I actually observe gives me some belief that they might actually be just lying and misleading people about how long it would take. So I'm going to make some rule here that's going to say how likely I am to believe them. And that rule is just going to say, if they are within what I would consider 95% of all the plausible outcomes, given how many times I've ordered from them, we're going to call it a wash. But if it's something rarer than 5% of all the possible outcomes, I'm going to call and complain about them misleading us about how long it takes to actually have food delivered. So we're going to go through the same set of steps. We're going to clearly articulate our beliefs. We're going to collect the data. We're going to compare it to the distribution that we think generates that data. And then we're going to determine if the discrepancy is big enough to change our mind about the delivery time. So we'll do these step by step. Our first step here is to clearly articulate our beliefs about the population. And the population here should be the population that is generating the travel time for them to deliver the food to my place. So when the restaurant tells me it takes them 30 minutes on average, that is a statement about the population, the true value that the restaurant knows for all deliveries. And so we need to be able to write a statement out that's going to break out the set of possibilities for the restaurant here that would allow us to find the set of data that is consistent with their claim and some things that are inconsistent with that claim. And the things that are consistent with that claim, we're going to call the null hypothesis. And everything else is going to show up here. That's going to be called the alternate hypothesis. And these have to be they have to have two properties. The first is that they have to be mutually exclusive, which means these two things cannot overlap at all. And they must be exhaustive, meaning they've covered every possible scenario. So our null hypothesis here is basically that the restaurant is exactly right, that the mean is delivery time is 30. The alternate would be that the delivery time is not 30 minutes. Our second step is going to be to calculate a statistic from the sample. And our statistic here is just going to be our sample average. So what we're going to do is we're going to have 25 pieces of data, n is going to be 25, that are going to allow us to calculate a sample average here. Now we're going to pick the sample average because in our last discussion of sampling distributions, we found out that the sample average was an unbiased and consistent estimator of the true population mean, which means it's relatable to the population value we're actually interested in. And the way it's relatable is via the central limit theorem. And the central limit theorem says that the distribution of sample averages that I could take out of any population are going to be centered around the mean mu. That's how we get that they're unbiased. And that the standard error, how broadly they are distributed around mu, is a function of both the underlying standard deviation of the data and the sample size. And so in our context, we can fill in all the pieces of information we have, and we know that sample averages are going to be normally distributed around the 30 minutes that the restaurant says it should take, with the standard deviation given by the 10 minutes in their standard deviation divided by the square root of the number of times we've ordered from them. Okay, so this is the square root of 25. Which means in English, we would say the average delivery time for a random sample of 25 orders should be on average 30 minutes, and the standard error is going to be about 2 minutes. Okay, it's going to be normally distributed around that. So how do we make the comparison to what we should have seen and to see if our average of 35 minutes is unreasonable? What we're going to do here is we're going to use the central limit theorem and our rule where we said we're going to give them the benefit of the doubt as long as what we see is within the 95% most plausible set of things we could if they were telling the truth. And so what we're going to do is we're going to use the sampling distribution to determine what the most likely 95% of average delivery times would be for a sample of 25 observations. And so to do this, we're going to identify what are going to be called critical values here. And the critical values are going to be the places that bound, okay, the 95% of the most plausible outcomes. And those are going to be in the middle of my distribution. So here I'm going to see one is going to be at the 2.5th percentile, another will be at the 97.5th percentile. The difference between those two is the 95% of the data that I'm after. Anything outside of that, we're going to call the rejection region. So let me just draw out, according to the central limit theorem here, our sample averages are going to be normally distributed around the mean that the company claims at 30 minutes. The standard deviation of that population is 10, our sample size is 25, which means what I can do is I can use the central limit theorem to figure out what sample average I would observe at the 2.5th percentile of the data and what sample average I would observe at the 97.5th percentile of the data. Now, if we were going to do that inside Excel, we would do that with the norm.inverse function, because we know that if we are told the area to the left of a point, we can recover the point in that distribution using this norm inverse function. And the arguments here are just the percentile of the data we're after, the mean of that distribution, and the standard deviation of that distribution. And it turns out that at 2.5th percentile, that is among the fastest 2.5% of all possible times that these people could get food to me if they were telling me that the average is actually 30 minutes, is about 26.8 minutes. Okay, that would be the fastest that random chance would generate. On the other hand, at the 97.5th percentile, we're now looking at the slowest times that we would expect just due to random chance, if they're telling the truth, would be about 33.92 minutes. And so what we're going to do is we're going to indicate what these critical values are on our distribution, and we're going to shade everything that is further away from the hypothesized mean. Okay, so we've said that we think the mean under the null hypothesis is 30. So we're going to shade everything above 33.92 and everything below 26.08. And these are what we're going to call the rejection region. Okay, because these two areas of my sampling distribution represent the least likely 5% of outcomes I could observe if the null hypothesis were in fact correct. And what we've already determined is we're willing to give them the benefit of the doubt for anything that falls in the 95% most common, but not the 5% least unlikely, or most unlikely, excuse me. And so the way we're going to tackle this is simply just to plot our sample average and see if that sample average falls in one of those rejection regions. And so again, we simply had a sample average of 35 minutes after our 25 orders. That shows up here in this right tail in this rejection region. So what does that mean? So since my sample average is in the rejection region, it's not among the 95% of values that would allow me to give them the benefit of the doubt. It is in fact among the 5% of values that I said are just too implausible for me to give them the benefit of the doubt anymore. And so what I have to do is reject the null hypothesis. I would say, given how long it's taken, given that I've ordered 25 times, this is a really, really unlikely outcome that it should take 35 minutes to get here, which means I'm going to call your bluff. You're not telling me the truth about how long it actually takes. It definitely does not take 30 minutes for the food to be delivered to me. Let's take a look at another problem here. Suppose that you're trying to fact check your boss who's promised that among your coworkers, you guys are going to receive an average of a 3% raise this year with a standard deviation of 1%. And so, not that you've got any reason not to trust your boss, but just the same, you chat with your the next people you run into, which happen to be about 16 coworkers, and you find out that between you and the other 15, the average raise in that group came out to be 2.75%. So you definitely trust your boss, and you don't want to confront your boss unless you're 99% certain you've been misled. So the question is, can you be 99% certain that you've been misled? Should you confront your boss? And so what we're going to do here is we're going to walk through the same steps. We're going to clearly articulate our beliefs about the population by stating a null and an alternate hypothesis. We're going to use the sample information we've collected from the 16 coworkers. we are going to use the central limit theorem to determine what set of sample averages we could have seen um, just out of sheer chance that would have been consistent with what your boss promised. And then we're going to determine if that 2.75% raise is among the 99% of things that we would have observed just due to sheer sampling error and chance. If it turns out that it is among that 99% of outcomes that are reasonable, we're going to fail to reject the null hypothesis. That is, we're going to say that it seems like what we've seen here is not enough evidence to contradict the boss's claim. All right, so what we're going to do here is we're going to let X represent the raise that each individual employee gets. The boss has made a claim that the average will be 3%. This is a claim about the full population of raises that would be passed out. And so what we need to do here is define a set of sample averages we could see that would be consistent with what the boss claimed and a set that would not be consistent. That is, we need to come up with the mutually exclusive and exhaustive way of partitioning all of the population averages we could see here. And so the baseline belief here, the null hypothesis, is that the average is 3%. And the alternate hypothesis would then be that the average is not 3%. So again, we're going to take our 16 employees, you and 15 of your colleagues. We're going to calculate the sample average of the raises. And what we're going to see is that that sample average is 2.75%. And so now what we're going to do is we're going to rely on what the central limit theorem should tell us about where those sample averages are likely to fall relative to the claim the boss is making about the 3% population average. And so what we're going to do here is we're going to plug in our information. We're going to say, well, the sample averages are normally distributed around the population mean under the null hypothesis, okay? Because the null hypothesis is what's going to tell us where our sample averages should actually show up. And so that is 3%. We know that the standard deviation in the population for raises is 1%, so that's what we've got right here. And the square root of n is the number of observations we have to calculate our sample average, okay? And so we had 16 employees from which we calculated our sample average X bar. In English, what we're saying is that the raise for any random sample of 16 observations will be normally distributed around 3% with a standard error of 0.25%. And so what we're going to do is we're going to find the middle 99% of observations that we would have seen according to the central limit theorem. These values of X bar at the 99.5th percentile and 0.5th percentile are what we're going to call our critical values. Okay, and they're going to define the boundaries for our rejection regions. Anything that we see that happens to show up in these red areas is going to be part of the rejection region. Now, to actually conduct the hypothesis test, all we have to do is see if our sample average, here 2.75%, shows up in one of these rejection regions. If it does, then it's among the least likely 1% of outcomes we could have observed if the boss was telling the truth. We can see right here that this 2.75 doesn't actually turn out to be that far away from the 3% claimed in terms of where it would fall in the sampling distribution. So since it's not in the rejection regions here, we're going to fail to reject the null hypothesis. Now we're going to move on to what are called one-tailed tests here. And what a one-tailed test is it's a way of looking at hypotheses where we do not have two rejection regions. So consider an example here. I tell you that you're going to spend no more than an average of 2 hours a week on homework. Well, I've made a claim that the amount of homework you're going to get is always going to be less than or equal to 2 hours, which means no matter how little homework I give you, I couldn't possibly give you so little homework that it would contradict what I'm claiming. That means there is only one set of sample averages that you could observe for the amount of time you spent on homework that could lead you to contradict my claim. And those would be very, very large values of homework. If I gave you 4 or 5 or 6 hours on average, that would contradict the claim. But even if I gave you 0, that would be an example of something that would be in one of the tails typically. It's not equal to 2. 0 is much less than 2. But since I've claimed here you'd have no more than 2 hours a week, what we're actually defining here is what's called a one-tailed hypothesis test. Now, these are going to look very similar. We're going to have the same steps to evaluate a hypothesis, but I'm going to talk you through the key difference here is in writing out the null and alternate hypothesis and then identifying where the rejection region is. Everything else is going to look exactly the same. So let's go through this problem. It says, I'm going to claim that you have no more than 2 hours of homework per week on average with a standard deviation of 1 hour. You go out and talk to 36 classmates, and on average, you spend 2.2 hours per week. You've decided as a group that you'll only confront me if you're more than 90% certain that I misled you. Do you decide to confront me about how much homework you've got? So let's go through these step by step. We're going to articulate our claims about the population. Now, the population here is going to be the true average number of hours spent on homework, but you only have a sample of data from 36 classmates. So we're going to say X is the number of hours spent on homework. I'm making a claim about the population that says it will be no more than 2 hours. And so again, we need to make a mutually exclusive and exhaustive statement. So the null hypothesis here would be mu is less than or equal to 2. That is, it is no more than 2. And the alternate is greater than 2. So again, we can see here that this partitions the set of possible outcomes into mutually exclusive. That is, there's no sample averages we could observe that would both satisfy the null hypothesis and the alternate hypothesis. And they're exhaustive. We've covered every possible sample average. So again, we're going to calculate our sample average from the 36 observations we have. This is the same as before. We're going to use the central limit theorem to determine what set of sample averages are plausible by plugging in the population mean under the null hypothesis, which is 2, the standard deviation, which is 1 hour, and the square root of the sample size here, which is the square root of the number of observations, or 36. So in English, the central limit theorem is telling me that the average hours spent on homework for any sample of 36 observations would be normally distributed around 2 hours with a standard deviation of 10 minutes. All right, so all I'm going to do here is I'm going to plot out what the central limit theorem would say. It's going to be normally distributed around 2 with a standard deviation of 1 divided by the square root of 36. And what we're going to do here is we're going to identify both the rejection region and we're plotting on where our sample average falls. So we said we want to find, you're only willing to confront me if you're 90% certain that I've misled you. So if you're 90% certain, what we need to do is find the 10% of values that are inconsistent with my claim that you would have less than or equal to 2 hours. And so in order to find things that are inconsistent with that, we need to find the set of 10% of sample averages we would observe that are much bigger than 2. So we're going to go as far right as we can and collect the 10% of observations here. And we know that that threshold observation right at the edge here will be at the 90th percentile then. Remember, the full area under this has to be 1, and so if there's only 10% of the observations to the right, that means the data point we are looking for here, that is our critical value, would be at the 90th percentile of this distribution. And we can again find that using the norm.inverse function where we plug in the percentile, the mean under the null hypothesis, and the standard error. And if we do that, we'll see that the sample average at the 90th percentile would be 2.21 hours. So if you were to go out and find a sample average among 36 classmates that was 2.21 hours or more, that would be unlikely enough, given what I have claimed, that you could be 90% confident that I had misled you. But lo and behold, with your sample average of 2.20 hours, we are just inside the plausible region that would not allow you to be 90% confident that I had misled you. So how do we actually interpret this? We're going to recognize that our sample average is not in the rejection region, which means we fail to reject the null hypothesis. So even though what I have given you for homework is bordering on suspiciously high, just on the edge of the set of things that would lead you to say with 90% confidence I had misled you, we're not quite there yet. If I gave you a little bit more homework, we'd push you over that edge. But for right now, 2.2 hours is not a high enough burden to reach, not a high enough level of proof to confront me about the amount of homework you're getting. So in summary, What we've learned is that since the central limit theorem tells us what we should observe from any population of data, we can see how implausible a sample average is. And so when we are testing ideas about what the true population average is, we use the central limit theorem to determine the plausible set of boundaries that fall with a particular set of confidence. For example, 99% confidence with our boss, or 90% confidence in confronting me, or 95% confidence in addressing our restaurant about their delivery. If it turns out that the sample average we observe is among one of these least likely outcomes that falls in the rejection region, we conclude that we must have been incorrect about our beliefs about the population.